Hello students, welcome back to today's lecture. So yesterday we have discussed something. Yesterday we have discussed about the first PDF in which we have talked about the internal energy. We have talked about the work done and we have talked about the heat. Today you may see this PDF which is corresponding to lecture number 2 which is there. And here in this case it starts with internal energy. So internal energy I explained yesterday only, and that you better know. So at last you may see that it is written du is equals to n into c into dt. So this is conditioned. Okay, हर केस में हम ये नहीं कह सकते हैं चेंज इन इंटरनल एनर्जी जो du है that will be equal to n into c into dt. Okay, that comes under the application of the first law of thermodynamics that we have to study now. Okay, तो वो du जो होगा n into cv into dt होगा, तब होगा जब हमारा क्या होगा, जब वर्क किया जाए at constant volume. Okay, so that will come during the explanation time. So now we talk about the applications of first law of thermodynamics. Okay, so here is the first application that we see in case of cyclic process. Okay, so here first point, or one can say the second point in this PDF is written cyclic process. Okay, so इसके ऊपर हम लोग एक heading दे सकते हैं. We can write one heading above this cyclic process, isolated system and isobaric process, that it is coming under the application of first law of thermodynamics. Okay, so now we define the isolated, or one can say the cyclic process. Okay, so yesterday we have talked about the thermodynamical processes, so under that only it comes cyclic process. So in that case of cyclic process we can say that during the process it is actually a circular type of process. Okay, in which the initial state from where the particle has started a change, okay, will be same as the when it is brought to will what will it again come back to the initial state again. Okay, after taking a round. So here how we define the cyclic process, it is defined about the system. Okay, so a system is taken from an initial state to the other different state, that what I can say, and finally brought back to the initial state. Okay, so such type of the process is known as cyclic process. Okay, so is case mein what will happen in case of cyclic process, the important thing is that key, since we know that internal energy is a state function. Okay, it depends upon the instantaneous state of the system which is there. Okay, तो किसी भी पॉइंट पे जहाँ पे हमारी प्रेशर, वॉल्यूम और टेम्परेचर का जो भी वैल्यू होगा वो हमारा डिसाइड करेगा क्या इंटरनल एनर्जी हमारा उस पॉइंट पे क्या है. Okay, so it is a state function. So according to this what cyclic process says that ki again the system is coming back to its initial state. So in that case the internal energy is what, initially it was something and now finally it was something, and both the something is not different but it is what same. ठीक है, यानी कि हम ये नहीं कह सकते हैं फाइनल स्टेट पे जो उसकी इंटरनल एनर्जी है वो क्या है, डिफरेंट है, बल्कि क्या है, वो फाइनल स्टेट पे जो इंटरनल एनर्जी है वो क्या है, सेम है, जो कि किसके बराबर है, दैट इज़ इक्वल्स टू द इंटरनल एनर्जी ऑफ द इनिशियल स्टेट. सो द चेंज इन द इंटरनल एनर्जी ड्यूरिंग द thermodynamical process will be equal to 0. Okay, so now we apply, you can see here the application of the first law is being done here, that is q is equals to delta u plus w, है ना. So in that case if I put delta u is equal to 0, so q will be equal to w. ठीक है, so here we can conclude that heat, whatever heat we are giving to the system will be equal to the work done by the system. Okay, and then next point which comes under the application of first law of thermodynamics is isolated system. Okay, so in this case what I can say, such system can neither do work nor can take or give heat or to the surrounding. Okay, so इस केस में क्या होगा, isolated system ऐसा system होता है that can neither do work nor it can what exchange the heat from the surrounding. Okay, so इस केस में भी क्या हो जाएगा, Q will be equal to 0. Okay, because the heat cannot enter also nor it can go what outside to the surrounding. So in this case according to the first law of thermodynamics what will be there, in this case the value of that delta u will be equal to what, 0. Okay, because q will be equal to w and w will be equal to 0. okay, because it can neither do work nor it can what, exchange the heat with the surrounding. तो Q भी जीरो होगा, W भी जीरो होगा. तो अकॉर्डिंग टू फर्स्ट लॉ ऑफ थर्मोडाइनमिक्स इस केस में भी क्या हो जाएगा, चेंज इन द इंटरनल एनर्जी विल बी इक्वल टू जीरो. So this is nothing but it is all the results are coming from the first law of thermodynamics that we better know. Okay, now we further talk about the isobaric process. So isobaric process is the process which is carried by the system at constant pressure, one can say. Okay, जिस भी केस में हमारा प्रेशर कांस्टेंट होगा, ठीक है, उस केस में हमारा क्या होगा, ड्यूरिंग द चेंज विल बी व्हाट, process will be said to be isobaric in nature. Okay, हम अगर एक एग्जांपल दें तो हम एक एग्जांपल दे सकते हैं किसका, द हीटिंग ऑफ अ वाटर इन अ बॉयलर, okay, of a steam engine and the formation of steam. Okay, so these all processes are coming under what, the isobaric process, because in this case the pressure is what, kept constant. Okay, so freezing of the water can also be one example. So many examples can be given here. Okay, so here I have shown one mathematical description is there, a small description is there, and about that you are very well aware that we have already seen in case of thermal properties of matter. Okay, तो यहाँ पे हम ये कर रहे हैं कि हम एक लिक्विड को ले रहे हैं. ओके, वी आर कंसिडरिंग वन लिक्विड, नॉट वन लिक्विड, we are considering a liquid of mass m that is converted into vapor. Okay, and all the conditions are at constant pressure and at constant temperature. ठीक है, so if I consider that latent heat of vaporization, ठीक है, उस केस में अगर हम हीट दे रहे हैं अपने m mass के लिक्विड को, तो there will be what, after some time what will happen, it will what, change into vapor. So there will be latent heat of vaporization that we have already discussed many times. So Q that I am giving for m mass, that will be equal to m into L और LV. ठीक है, तो ये कोई नई चीज़ नहीं है जो हम लोग पढ़ रहे हैं. ठीक है, इसको वी हैव ऑलरेडी स्टडीड इन थर्मल प्रॉपर्टीज़. And what will be the work done? We know that earlier it was what, it was in a liquid state, and finally it is what, going to in that what, vaporized state. Okay, तो V of V जो हमारा क्या है, वॉल्यूम इन अ वेपर स्टेट. ओके, एंड V of L इज द वॉल्यूम ऑफ H2O इन द लिक्विड स्टेट. तो ये हमारा कुछ नया नहीं है, वर्क डन हम लोगों ने कल पढ़ा है, दैट इज इक्वल टू P इंटू डेल्टा वी. तो डेल्टा वी हमारा क्या होता है, चेंज इन द वॉल्यूम, तो वेपर माइनस liquid. Okay, that is the change, V of V minus V of L, that is the change in the volume, and into P, that will be work done. Now applying again the first law of thermodynamics, that is Q is equals to delta U plus dW. Okay, so that will be equal to M into LV, that is written in the bottom, you can see here. ठीक है, यहाँ पे लास्ट में लिखा हुआ है इस पेज में, M into LV is equals to delta U plus P into V of V minus V of L. Okay, so this is the condition which we have obtained, okay, according to that first law in case of isobaric process. Okay, now next we talk about the process that is known as isochoric process. Okay, so तो यहाँ पे तो हम लोग एप्लीकेशंस के बारे में बात कर रहे हैं corresponding to different thermodynamical process of first law. Okay, later on we will be talking about the work done. Okay, so we talk about the work done also, in some of the processes. So here we talk about the isochoric process. So in this case we can say that isochoric process is carried at constant volume. Okay, so in this case delta V will be equal to, or one can say change in the volume will be equal to 0. So work done will also be 0 because it is what, P into delta V. Okay, then we use the first application. Okay, we use the first law of thermodynamics, that is Q is equals to delta U plus dW or W. So according to that it will give what, when W will be equal to 0, so Q will be equal to delta U. That means the entire heat that we are giving to the system is used to increase the internal energy. Okay, so this is the condition of what, isochoric. Understood? Next we talk about the isothermal process. So in this isothermal process we also talk about the work done. Okay, that is the work done. What is the work done calculation in case of iso. So now we talk about isothermal process and the work done in this. Okay, so here isothermal process corresponds to the process which is carried at constant temperature. Okay, so here it is written also, for isothermal process the temperature is kept fixed when a system is carried from initial state to final state, or one can say stage also. Okay, so for isothermal process here we consider that ideal gas is there है ना, and the initial state is what, P1 V1. okay, यहाँ हम केवल P और V के बारे में बात कर रहे हैं. वी आर नॉट टॉकिंग अबाउट द राइट नाउ नंबर ऑफ मोल्स एंड ऑल दोज थिंग्स. ओके, so we consider that the state of the system in the first stage is defined by P1 V1, and then when system has moved on to the next stage, जब उसमें कोई changes हुआ होगा, next stage पे पहुंचा होगा, तो उस केस में we consider that the pressure is P2 V2. ओके, बीच में कॉमा होगा P1 V1 के भी और P2 V2 के भी. okay, so we know that ideal gas equation is what, PV is equals to mu RT. here it is written that. okay, so यहाँ से हम P लिख सकते हैं in terms of mu RT and V. okay, so we better know that work done formula is what, integral of P into dV. ठीक है, और V चेंज कहाँ से कहाँ तक हो रहा है, एक निश्चित वॉल्यूम है उसकी, देखो चेंज होने की, एक स्टेज से दूसरे स्टेज तक. ठीक है, पहले V1 वॉल्यूम था, फिर बाद में क्या हो गया, V2 वॉल्यूम हो गया. इसीलिए over this integral this V1 to V2 is applied here. okay, because it is a definite integral, the change is definite. ठीक है, then it is bounded. okay, so here we again place the value of P, that is mu RT upon V into dV. तो हमें ये पता है mu is also constant, R is also constant, and temperature is also constant, because this is what, isothermal process. and integral of V1 to V2 into dV upon V. okay, and we better know that many times I said you है ना, in class also we have done that, अगर हम integral of dx upon x करते हैं, इस तरह से यहाँ पे dv upon v लिखा है, तो वो क्या देता है, log x देता है अगर वेरिएबल x है. पर यहाँ पे वेरिएबल क्या है हमारा, ओवर v है, dv है. ओके, dv अपॉन v लिखा हुआ है, तो हमारे log x की जगह क्या आ जाएगा, log ऑफ v आ जाएगा. ठीक है, यहाँ पे ln लिखा हुआ है ना, log बेस e. ओके, सो इट इज़ व्हाट, lv. okay, and limits we have to apply it. okay, after on this bracket, that is from v1 to v2. ठीक है, तो फिर हम उसको क्या करेंगे, w को हम लिख सकते हैं म्यू r इंटू टी, और हम उसमें हायर लिमिट अप्लाई करते हैं लॉग में पहले, दैट इज़ ln v2, है ना. क्या लिखेंगे, म्यू r इंटू टी, ब्रैकेट में क्या लिखेंगे, ln v2 माइनस ln v1. ठीक है, और फिर वो क्या होता है, log a माइनस log b क्या होता है, log ए अपॉन बी. ठीक है, तो ए की जगह V2 है और बी की जगह V1 है. तो हमने वही सिंपल फार्मूला इस्तेमाल किया है जो हम लोग कई बार कर चुके हैं, पढ़ चुके हैं, दैट वी हैव ऑलरेडी डन. ओके, सो ln v में हम v अप्लाई द फर्स्ट लिमिट, दैट इज़ V2 फर्स्ट, that will give what, ln V2 in the bracket minus ln V1 after applying the second limit. okay, so this is the required work done that you have to know. okay, or you may learn it also, that is the work done formula that will be applicable in the numerical part. okay, so here we can say that the constant temperature is there in case of isothermal process, and we know that कि हमारा जो इंटरनल एनर्जी का चेंज होता है वो किसका फंक्शन होता है, वो टेम्परेचर का फंक्शन होता है. ठीक है, हमने लिखा था ना, अभी ऊपर देखोगे तो यहाँ पे लिखा गया था ना, दैट इज चेंज इन द इंटरनल एनर्जी डी यू इज इक्वल्स टू एन इंटू सी वी इंटू डी टी. यहाँ पर सी वी होगा. ठीक है, तो देखो जो चेंज है डेल्टा, या हम कह सकते हैं डी यू है, वो किसके फंक्शन में है, डी टी के फंक्शन में, यानी कि चेंज इन द टेम्परेचर. तो आइसोथर्मल प्रोसेस में देयर इज़ नो चेंज इन द टेम्परेचर, सो दैट मीन्स डी टी विल बी इक्वल टू ज़ीरो. तो यहाँ से डी यू क्या हो जाएगा हमारा, ज़ीरो हो जाएगा. सो हियर डी यू मीन्स डेल्टा यू. तो अकॉर्डिंग टू फर्स्ट लॉ ऑफ थर्मोडाइनमिक्स, जब डेल्टा यू ही हमारा ज़ीरो हो गया तो क्यू विल बी इक्वल टू डब्ल्यू. ओके, सेम थिंग इज डन हियर ऑल्सो इन केस ऑफ एडियाबेटिक प्रोसेस. ठीक है, इन सच प्रोसेस वी कैन से दैट द change is what in that system, है ना, with respect to that surrounding, under which condition, under under the condition in which there is no heat exchange, okay, in between the system and the surrounding. Or one can say in this process which is taking place in a system, heat can neither enter the system nor leaves it out. okay, or nor it can leave it. okay, so such a process is known as adiabatic process. So in this case again we apply, okay, and that first law of thermodynamics. So in that case delta u will be equal to minus of dw, or one can say minus of w. okay, so this is the case. In this case what will happen, w will be what, one can say is negative. okay, when delta u is coming, how much, it is coming what, when W is what, positive, okay, then delta U will be negative. So that is another thing, but according to this PDF, for adiabatic process the important condition is that you can see that is PV to the power gamma, यहाँ पे लिखा हुआ है ना, PV to the power gamma is what, constant, ठीक है. So this condition you shall know, okay, about adiabatic process which is there, and gamma is nothing but it is a constant, and it is the ratio of the specific heat at constant pressure and at constant volume. So ये हम लोग we have already studied in thermal properties of matter, that is what is Cp and what is Cv, okay, that is the specific heat of the gas at constant pressure, that is Cp, and here Cv is the specific heat of the gas at constant volume. So again applying the same formula for the work done, that is integral V1 to V2. अगेन यहाँ पे चेंज कहाँ से हो रहा है, V1 वॉल्यूम से V2 वॉल्यूम तक हमारे सिस्टम का चेंज हो रहा है, एंड PdV, एंड वी रिप्लेस हेयर द वैल्यू ऑफ दैट P, ठीक है, फ्रॉम द इक्वेशन नंबर 1, दैट इज कांस्टेंट अपॉन V टू द पावर गामा, एंड अगेन द सिंपल इंटीग्रेशन इज डन, ठीक है. अगर V टू द पावर यहाँ पे अगर माइनस गामा इंटू डी कर दिया जाए, क्योंकि V टू द पावर गामा इज इन देयर इन द डिनोमिनेटर, ओके, जब वो उसके ऊपर जाएगा, ठीक है, जब डी के साथ जाएगा तो क्या लिख सकते हैं हम, इंटीग्रल ऑफ V पावर माइनस गामा इंटू डी लिख सकते हैं, ठीक है. यानी कि कुछ इस तरह का जो बॉक्स में लिखा है, देखो, इंटीग्रल ऑफ x टू द पावर a dx इज इक्वल्स टू x टू द पावर a प्लस वन अपॉन a प्लस वन. सो दिस इज द स्टैंडर्ड फार्मूला दैट इज एप्लीकेबल हियर इन दिस इंटीग्रेशन, ओके. तो ये तुम्हें याद करना पड़ेगा इफ़ यू आर नॉट नोइंग दिस, ओके. सो हियर a इज़ द कॉन्स्टेंट जो पावर में है, और x हमारा क्या है, वेरिएबल है जिसके ऊपर इंटीग्रेशन लगा है, ठीक है. तो यहाँ पे देखो x की जगह क्या कर दिया गया है, v को ले लिया गया है, और पावर की जगह क्या मान लिया गया है, गामा को ले लिया गया है. तो जब v पावर गामा ऊपर जाएगा तो दैट विल बी व्हाट, v टू द पावर माइनस गामा, ओके. सो नाउ इन प्लेस ऑफ a देयर इज व्हाट, माइनस गामा, okay. So again applying this formula which is there in the box, so you will get this result, okay, and the common substitution is done now based upon that equation number 1, ठीक है. तो जहाँ जहाँ पे हमारा v टू द पावर देख सकते हो कि कांस्टेंट को यहाँ पे अप्लाई कर दिया गया है, ठीक है. तो कांस्टेंट इज व्हाट कमिंग इनसाइड आल्सो, ठीक है. सो कांस्टेंट माइनस कांस्टेंट यू कैन सी इन दिस ब्रैकेट ना, here you can see. So this is the constant corresponding to, one constant can be corresponding to P2 V2 and one constant corresponding to P1 V1 state, okay. So उसी के corresponding हम जो जनरल फार्मूला है एडियाबेटिक का, PV टू द पावर गामा कांस्टेंट हम लिख सकते हैं P1 V1 के लिए भी और P2 V2 के लिए भी. तो वहीं पे यहाँ पे देखो कांस्टेंट को रिप्लेस किया गया है, एक कांस्टेंट को P2 V2 टू द पावर गामा लिखा है, एंड वन कांस्टेंट इज रिटन एज P1 V1 टू द पावर गामा, लाइक दिस, ओके. So now further it is reduced, and here the value of the work done is coming, that is mu into r upon 1 minus gamma into t2 minus t1. So this derivation is important, okay. So this you shall know, and the final result you shall also know about the work done, understood. So now further we talk about the difference in the molar specific heat, okay, of an ideal gas. So our study is based upon this only, on ideal gas, okay. So here you can see that one is the molar heat capacity, or one can say the specific heat capacity at constant pressure, that is Cp, and the other is Cv, that is specific heat capacity of the ideal gas at constant volume. So for both the case we use the first law of thermodynamics, and we get this formula, that is Cp minus Cv is equals to R. It is written in the last, okay. This is also known as the Mayer's relation, okay, and this is very important relation that you shall learn, okay. So here the derivation is done based upon that first law, that is here it has been taken for 1 mole of an ideal gas. So first at constant volume it has talked, so delta V will be equal to 0, okay, dV is equal to 0, it is written there. So according to first law, जब dV 0 हो जाएगा तो वर्क डन क्या हो जाएगा, that will be 0. So dq हमारा किसके बराबर हो जाएगा, du के बराबर हो जाएगा, ओके. और du हमारा किसके बराबर हो जाएगा, that will be Cv, that is into dt, ठीक है. जो यानी कि हीट जो होगी हमारी Cv इंटू डी टी, वही हमारे किसके बराबर हो जाएगी, इंटरनल एनर्जी के बराबर हो जाएगी, ठीक है. तो डी क्यू इज इक्वल टू Cv इंटू डी टी, दिस इज देयर, ओके, ये होता है, ओके. दिस वी हैव ऑलरेडी स्टडीड इन थर्मल प्रॉपर्टीज ऑफ मैटर, ठीक है. जिस Cv को हम डिफाइन करते हैं डी क्यू अपॉन टी के टर्म्स में, ओके. सो फर्दर this is equation 1. Again it has applied the first law of thermodynamics, dq is equals to du plus dw at constant pressure, ओके. सो एट कांस्टेंट प्रेशर अगर हम बात करते हैं तो उस केस में क्या हो जाएगा, डी क्यू सी पी इंटू डी टी हो जाएगा, ओके, इज इक्वल्स टू व्हाट, डी यू प्लस पी इंटू वी टू माइनस वी वन। अब यहाँ पे हमारा क्या हो जाएगा, कांस्टेंट वॉल्यूम के बारे में बात नहीं कर रहा है, इसीलिए यहाँ पे हमने वर्क डन लिया है पी इंटू वी टू माइनस वी वन। ओके, तो हियर यू गॉट इक्वेशन नंबर 1 corresponding to at constant volume, and here you got equation number 2 corresponding to constant pressure. ओके, सो दोनों का ही corresponding C की वैल्यू क्या होगी, बदलेगी, क्योंकि एक में CP होगा, दूसरे में क्या होगा, CV होगा, at constant pressure and at constant volume. So we are subtracting equation 1 and 2 and you finally get this value, that is Cp minus Cv is equals to what, R. And here it has the ideal gas equation has been applied for 1 mole, that is Pv is equals to RT. म्यू की जगह 1 हो जाएगा, इसीलिए RT लिखा गया है। ओके, और दोनों को ही डिफ्रेंशिएट किया गया है दोनों तरफ, ठीक है। तो इधर प्रेशर हमारा कांस्टेंट था और वॉल्यूम को वेरिएबल माना गया है, इधर टेम्परेचर का चेंज में डिफ्रेंशिएशन किया गया, आर कांस्टेंट बाहर आ गया है, ठीक है। तो डिफ्रेंशिएशन पी वी इज इक्वल टू आर टी में किया गया, एल एच एस और आर एच एस में। तो पी को छोड़ दिया है, उस पर डिफ्रेंशिएशन अप्लाई नहीं होगा, तो वी पे होगा, इसीलिए पी इंटू डी वी लिखा है। और आर पे नहीं होगा क्योंकि आर इज कांस्टेंट, सो डिफ्रेंशिएशन इज ओवर टी। ओके, so from here we get the equation number 3, that is Cp minus Cv is equals to R, and the value of R is what, fixed. Okay, that is equals to 1.99 calorie per mole per Kelvin. Okay, it is approximately written as 2 also sometime. Okay, so this was about the difference in the specific heat of an ideal gas, and this should be learned, this mere formula should be learned. Okay, now further we talk about the degree of freedom. Okay, and degree of freedom is nothing but it is total number of the independent motion that the particle can make. So for this the explanation can be done. So about that degree of freedom, I already told that it is nothing but it is the total number of independent, one can say, motion which a particle can make, you know, as it is written there in the PDF also. So here we can define that degree of freedom can be for three different types of the gases that are there in the nature. Okay, first is what, the monoatomic gas, and then for the diatomic gas, and then for the polyatomic, or one can say the triatomic gas which is there. So here you can see some figures which has been drawn there. Okay, I hope that it is visible to everyone. So for that this you may write. Okay, जो भी हमने इस पे वीडियो में लिखा है इसको तुम लिख सकते हो अपने उसमें। तो दिस इज़ माई हैंड रिटन नोट्स। ओके, सो हियर यू कैन सी दैट डिग्री ऑफ फ्रीडम फॉर अ मोनोटॉमिक गैस, यानी कि जिसमें एटम क्या होते हैं, 1 होते हैं, ठीक है, उनको हम क्या बोलते हैं, दैट इज सपोज टू बी व्हाट, द मोनो, ठीक है, दैट आर सपोज टू बी मोनोटॉमिक गैस। फॉर एग्जाम्पल द इनर्ट गैसेज आर देयर, हीलियम, सॉरी वन कैन से आर्गन इज देयर ना, हीलियम इज देयर, एक्सेट्रा इज देयर. So all these are what supposed to be what, monoatomic. Okay, similarly for diatomic also I can consider, that is H2O2 etc. ठीक है, तो ये हमारे क्या होते हैं, डायटोमिक मॉलिक्यूल्स हैं, जिसमें 2 एटम्स तुम देख सकते हो, उसमें एक एटम है तुम्हारा, ठीक है, एंड हियर देयर आर व्हाट 3 एटम्स विच आर देयर. Okay, so all the atoms are what can be seen in case of what, 3D. Okay, it have the 3D motion. Okay, suppose that ki if I place any gas molecule inside a room, so it can moves in 3-dimensional way. Okay, so same is that for the molecules also. तो यहाँ पे हम मोनोटॉमिक के बारे में अगर बात करते हैं तो it can moves along x axis also, it can move along y axis also, it can move along the, one can see, z axis also. So here the total, so here one can say it has what, it has total 3 translational, okay, degree of freedom. Okay, 3 translation motion along the 3 different axes which is there. And similarly here is no it cannot, it doesn't have any axis, okay, about which it can rotate. Okay, but in case of this you can see there is a line joining in this case of diatomic molecule. Okay, this is a line joining between the 2 atoms. For example, if I consider the O2 atom, okay, so it can rotate about any axis, okay, any of the 2 axes like this. So about this axis also it can rotate here. So here the rotation direction is shown here, you can see. Okay, but it cannot, the axis is not perpendicular to this x-axis, so it cannot rotate about this. Okay, so it can translate along x-axis, okay, but it cannot rotate about that. Okay, so perpendicularly it can rotate about this y-axis, and perpendicularly it can rotate about z-axis also. So 2 rotation is done, and by the same time it can what, translate also along z-axis, and it can translate along y-axis. So here you can see it can show the translation motion along x, y and z, as well as it can what, rotate about y-axis and z-axis, but it can't what, have its rotation about the x-axis. Okay, because it is not, the bond is not perpendicular to that. Okay, So correspondingly, the total degree of freedom will be what, 5 in this case, because 3 translation and 2 rotational. Similar goes for this triatomic molecule, or one can say polyatomic molecule. Okay, so here this is the molecule arrangement that you can see, and this is the origin of that Cartesian coordinate. Okay, so here it can rotate about the 3 axis, okay, as well as it can translate about the 3 axis. That's why it is written 3t plus 3r, that is 3 translational plus 3 rotational degree of freedom. Okay, now the very important thing which is here we are going to discuss, that is evaluation of molar specific heat, that is Cp comma Cv, and ratio of specific heat, that is Cp upon Cv of gases. So here we again start our discussion with the previous topic that we have already studied. So yesterday we have talked about the internal energy. ठीक है, तो अगर हम if I talk about the 1 mole of the internal, so here if I talk about the 1 mole of the internal energy of the gas, so we write for 1 mole हमें ये पता है कि total number of the atoms are Na, that is the Avogadro number. ठीक है, so U will be equal to of the gas N into 1 by 2 F of K into, या K भी हम कह सकते हैं, into T, that is the Boltzmann constant, और इसी को हम क्या लिखे थे, half into F into R into T. ठीक है, this is nothing new. Okay, so this into this will be equal to R, that is the universal gas constant. Okay, so this we have seen. So again if I differentiate the above equation, so du upon dt will be equal to how much, du upon dt will be half of F into R. Okay, so name this equation number 1. So now further if I talk about the gas, if I suppose that if I am giving heat to the gas and it is what, expanding, gas is expanding and there is the change in the temperature obviously, तो temperature का change हम मान लेते हैं dt मान लेते हैं, तो dq उस केस में क्या हो जाएगा, at constant volume, at constant volume. ओके, at constant volume dt हम ये मान रहे हैं चेंज है, और at constant volume क्या होगा, टेम्परेचर होगा, और at constant volume dq क्या हो जाएगा, dq will be equal to cv into dt हो जाएगा. ओके, दिस विल बी cv into dt. सो अकॉर्डिंग टू द फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स, ठीक है, या फिर हम ये कह सकते हैं dt इज अ चेंज इन द टेम्परेचर लाइक दिस. ओके, dq की वैल्यू इतनी हो जाएगी. ओके, तो वी अकॉर्डिंग टू द फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स व्हाट आई कैन से दैट du इज इक्वल्स टू, du किसके बराबर हो जाएगा, du विल बी इक्वल टू cv इंटू dt, बिकॉज 1 मोल, तो n की वैल्यू क्या हो जाएगी, 1 हो जाएगी, तो हम du को इसके बराबर लिख सकते हैं अकॉर्डिंग टू फर्स्ट लॉ, क्योंकि हमारा du किसके बराबर होगा, dq के बराबर होगा. कांस्टेंट वॉल्यूम है तो वर्क डन क्या हो जाएगा, दैट विल बी व्हाट, 0. ओके, so cv will be equal to du upon dt. Okay, so from here we can write that there is a relation of cv that comes equals to 1 by 2 F into R. ठीक है, according to the equation number 1 and 2, this relation we can write. Okay, that is from equation 1 and 2. Okay, from equation number 1 and 2 this relation we have seen. Okay, so now we know that Mayer's formula. Okay, तो हमें पता है, ठीक है, we know Cp minus Cv is equals to what, R, जो भी हम लोगों ने थोड़ी देर पहले पढ़ा है, this we have already discussed, okay, few moments back. So from here Cp, what I can write, if I put this value of Cv here, so we get the value, okay, that is equals to F upon 2 plus 1 इंटू आर. ये हमारे किसकी वैल्यू आ जाएगी, सी पी की वैल्यू आ जाएगी. सी वी हमें पता है, इसमें हमें पुट करना है. दिस इज द मेयर्स फॉर्मूला दैट वी ऑलरेडी नो. ओके, सो दिस इज इक्वल्स टू 1 प्लस एफ अपॉन 2 इंटू आर. ओके, दिस इज वेरी इंपॉर्टेंट. ऑल्सो we know about the gamma, that is equals to cp upon cv. this also we have seen. okay, so इसको जो हम इसमें पुट करेंगे, f upon 2 into r, these are the values एफ आर बाई 2, तो हमें क्या मिलेगा, गामा की वैल्यू यहाँ से मिलेगी, दैट विल बी इक्वल टू 1 प्लस 2 बाई एफ. ओके, so this is the required value of the gamma, where f is the degree of freedom that you know. Okay, this is the degree of freedoms, and you better know the degree of freedom for all the molecules which are there. Okay, even for the monatomic also you know for the diatomic, and you know for the polyatomic or triatomic molecule. ठीक है, so further we talk about the monatomic मोनो एटॉमिक गैसेस के बारे में जब हम बात करेंगे तो वी कैन राइट द वैल्यू ऑफ सी वी। तो सीधे हमें क्या है, सी वी की वैल्यू कितनी है हमारी, दैट इज इक्वल्स टू हाउ मच, एफ आर अपॉन टू। तो वी know that F is what, 3 for monatomic, R is R, and 2 will be 2. So this will be what, CV will be equal to 3R upon 2. Okay, that's equal to 3 calorie per mole per Kelvin. Okay, and CP will be equal to F by 2 plus 1 into R is equals to F R upon 2. ठीक है, ये किसके बराबर हो जाएगा, 5 कैलोरी पर मोल per Kelvin. Okay, and what will be the value for gamma? Similarly, gamma also you can calculate. Okay, so gamma you can calculate. So gamma will be equal to, simply you have to place in this formula the degree of freedom. So it will be coming, I think so it will be coming 5 by 3. So normal substitution you have to do here. Okay, and like this you can try for, this is for monatomic that we have done. Okay, you can try for diatomic also, you can try for triatomic also. Okay, so individually, that is your homework, that you shall try by your own, that how much CV is coming, how much CP is coming, and how much gamma is coming for diatomic also and for polyatomic also. Okay, and all these values you shall learn, ये सारी values तुम्हें याद होनी चाहिए. Okay, because these will be helpful in the numerical part. Okay, so I hope that you have understood today's lecture. So many things I have written here. So all these formulas for the competitive point of view also you shall know. Okay, about CP and CV, and this Mayer's formula is also very important. तो जितने भी हमने डबल टिक किए हैं ये सारे तुम्हें याद होने चाहिए. Just make a short notes about this. Okay, and the CP and CV, what is CP for the monatomic gas, what is CV for monatomic gas, and what is the value of gamma for monatomic gas. Okay, for diatomic gas that you can do by your own, that what I told, for polyatomic also. Okay, so let this much be for today. Thank you.